Okay, today we're going to be talking about Newton's law of cooling and heating. This is a example of a real-world problem application, which is a transformed exponential function. So an exponential function that's been shifted around a little bit. And basically it says if we place an object in an environment that's a different temperature than the object was when it started, and if we can hold the temperature of the environment constant, then the temperature of the object will heat up or cool off as necessary to eventually approach the temperature of the environment. And the rate of this change in temperature is proportional to the difference in temperature from the constant environmental temperature T sub A. And it turns out that if that's the case, then this is the formula that you get here, is that the temperature of the object, capital T, is T sub A, the temperature of the ambient temperature of the environment, T sub A, plus the initial difference in the initial temperature minus T sub A, times e to the kt, where k is some constant. So we have three constants here. We have T sub 0, T sub A, and k. T and T are your variables. Now notice I'm using lowercase t for the time, uppercase T for the temperature. The k, the T sub A, and T sub 0 are constants. So in mathematics we use a lowercase letter and an uppercase letter are two different variables. So capital T is going to be the temperature of the object at any particular time. Little t is the time. T sub 0 is the initial temperature at time t equals 0. T sub A is the constant ambient temperature of the environment. And k is going to end up being a negative number, and it's a rate which is constant. So the coefficient of the exponential term, T sub 0 minus TA, is the initial difference in temperature and the environment. Since k is negative, e to the kt is going to get smaller and smaller and smaller as t gets larger and larger and larger, and so e to the kt is going to approach 0 as t approaches infinity. So as t goes towards infinity, this e to the kt is going to approach 0, so this whole term here is 0, approaching 0, and then we add that to T sub A. The temperature approaches T sub A, which makes sense. If you leave an object long enough in a certain temperature, it's going to move to the temperature of the environment. Now we're assuming, of course, that that object doesn't have a heat source of its own. Like a human body, our metabolic processes keep our temperature at a constant, approximately 98.6 degrees Fahrenheit. So that wouldn't apply to us if we're, living human being. But you put a cold food in a hot oven, keep the oven the same temperature, that'll heat up. The food will heat up if you leave it in there long enough to the temperature that the oven is. If you pour a hot cup of coffee and then set it down outside in the cold, the coffee will cool off to the temperature of the outside. So it works for both heating and cooling. If the temperature is, and I'll do an example of each one here in a minute. So if it's initially hotter than the environment, the initial difference T sub 0 minus TA is a positive number, and the temperature is always a bit above the ambient temperature, so you're always adding a little bit to the ambient temperature, but the amount you're adding decreases as the object cools off. But if the object is initially cooler than the environment, then the initial difference T minus T sub 0 is negative, and the temperature T is always a bit below the ambient temperature. It'll be colder and then warms up towards the ambient temperature. Either way, it levels off an asymptote of y equals T sub A. Technically, in this formula, it never really reaches that asymptote, but in practicality, it's so close that you can't tell the difference. We are assuming that the temperature of the environment stays the same. So let's look at a Newton's law of heating example. A potato is at room temperature, let's say that's 70 degrees Fahrenheit. It's placed in an oven that's preheated to 450 degrees Fahrenheit. The oven stays at the same temperature all the time. So 15 minutes after being placed into the oven, the potato has been heated to a temperature of 100 degrees. So let's see if we can write a formula for the temperature T of the potato, capital T, as a function of the time, little t, since it was placed in the oven. So T equals 0 is the time it was placed in the oven. T in general is the amount of minutes, let's do it in minutes, after being placed in the oven. Now the first sentence right here tells you enough that you can figure out two of the constants are actually placed in there. So room temperature of 70 degrees Fahrenheit is the initial temperature when it's placed in the oven. So that's T sub 0 is 70. So you can see I substituted 70 there. The 450 is the ambient temperature of the room, which is placed in here twice, both right here and over here. So 70 minus 450 is negative 380. Okay? So it's 380 degrees below the ambient temperature of the oven. And the 450 is here. So this is our equation. The only problem is we're still missing one of the parameters k. So there are three parameters in the original, three constants that we need to figure out, T0, TA, and k. And then once we know those, then we have variables, little t and capital T, that can vary. So to find that other k, that's why we need one more point on the curve, 15 minutes, 100 degrees. And so we can plug that in, 100 for t, capital T, 15 for lowercase t. So this exponent is 15k. I'm going to subtract 450 from both sides, and we get negative 350 equals 380. Negative 380 e to the kt, or e to the 15k. Divide both sides by negative 380, and I'm going to reduce a little bit here. First of all, the negatives cancel. We can divide both the top and bottom by 10, and you get 35 over 38 is e to the 15k. Take this and rewrite it as a logarithm. 15k equals the natural log of 35 over 38. Solve for k by dividing by 15, and we see k is natural log of 35 over 38 divided by 15, and I did that on a calculator and got approximately negative 0.00548, whatever. K should always be a negative number. So notice that we're measuring time in minutes and temperatures in degrees Fahrenheit. So plugging that in, here's our formula. T equals 450 minus 380 e to the power, natural log of 35 over 38, whole thing over 15 times t, all that's the power. And I graph it over a reasonable time. In this case, this formula doesn't start applying until we put the potato in the oven at time 0. So our x is going to start, or t in this case, is going to start, lowercase t is x, or input, is going to start at 0. And I went ahead and went like 600 minutes, which is like 10 hours. We're not going to bake the potato that long. But, if we left it in there 10 hours, this is what the graph would look like. And notice that it's exponential, it's coming up, and it's leveling off to a horizontal asymptote at 450, which is this grid line right here, not the very top one, but the next one over, next one down. And if we go out far enough, you'll see it looking like that asymptote. So this seems like a reasonable thing. What's the temperature after cooking 1 hour? Well, we just want to put in 60 minutes here and see what the y is, and we can see about what it is there. And so we just plug that in here, 60 for little t. Well, 60 divided by 15 is 4, so that I can simplify that a little bit. And I can go ahead and type that one in right there, just like it is on the calculator, and that's what I did here in the second part here. 450 minus 380 e to the power, parentheses, 4 times ln of 35 over 38, close the parentheses, close another parentheses there, and then we get 176.5226345 minutes. Temperature, that's Fahrenheit. And the minutes are 60. 60 minutes are 1 hour. We know it's about 177 degrees Fahrenheit in 1 hour. I also want to point out that if this is e to the log whatever, then to the fourth, so e to the log cancel each other out, and I get 35 over 38 here for the base, and that's to the power 4. So I could also get rid of the e's and do it that way, and in fact in general it is 450 minus 380 35 over 38 is the base, and the power is t over 15. So 60 over 15 is the 4. Type it in that way like I did the first one up here, and you get the same thing. So you can do that reduction using the properties of logarithms or not. It doesn't matter. You still get the same thing. You get 177 degrees in 1 hour. And the next one, when does it first reach 150 degrees? So, by the way, 1 hour up here on this picture is, if we had this in our calculator, we could just do a trace and type in 60 for x, and it should come up with that same y. If we want to go backwards, do it out calculator ways, like this one where we reach 150, we'd find 150, which is this grid line here, and come down and see where it crosses here. It looks like it's 40 something, and so we could do that. We can also do it algebraically. Again, we're just plugging in 150 for the capital T, the temperature. Okay, subtract 450 and we get negative 300. Negative 300 over 380 reduces to 15/19. Take the logarithm there, rewrite it as a log. Log of 15/19 equals the power. Multiply by 15 and divide by this log over here, and we get t is 15 times the natural log of 15/19 divided by natural log of 35/38. And that's what I've got typed over here in the computer calculator screen you can see over here. And that turns out to be 43.1166, whatever. So about 43 minutes, the potato will be 150 degrees. Alright, here's an example of Newton's law of cooling. You might see this on, all the cop shows or whatever. CSI. A crime scene investigator arrives on the scene of a murder. At 2:00 p.m. she takes the temperature of the victim's body and finds it to be 85 degrees Fahrenheit. 1 hour later, she again takes the temperature of the body and finds it is now 80 degrees Fahrenheit. She walks over the thermostat and notices it's set to 68 degrees Fahrenheit. If we assume the heating cooling system is working to keep it at that temperature, can we estimate the time of death? Well, we see this as a Newton's law of cooling problem because once the body dies, it's no longer generating its own heat, and the ambient temperature of the room here, okay, T sub A, is 68 degrees, and we're assuming, of course, that 68 degrees is held constant. So with that assumption, let T be the time since 2:00 p.m. when the initial temperature measurement was made. Okay, so we are going to have some negative time here. In fact, the time of death is going to be a negative time. Okay, so it's still the same formula. T equals T sub A plus T sub 0 minus T sub A times e to the kt. The T sub 0 is our initial temperature at the first measurement, which was 85 degrees. The ambient temperature of the room is 68. And that gives us this setup here. 85 minus 68 is 17. So we have our formula is capital T equals 68 plus 17 e to the kt. We don't know k yet. So that's why she had to take the second measurement. So the second measurement said it's now 80 degrees Fahrenheit 1 hour later. So we're measuring time in hours. T is 1. The temperature is 80. We plug that in. Subtract 68 from both sides. We get 12 equals 17 e to the kt. 12/17 is e to the kt, or e to the k, because t was 1. And rewrite as a logarithm. K is the natural log of 12/17. So that's the k, which I can plug in. And now our formula is t equals 68 plus 17 e to the natural log of 12/17 t. And we notice that's an exponential decay function. It's decaying, but approaching an asymptote of 68. So it's coming down. Now, we also know that the temperature of the body when it died was at least approximately 98.6 degrees Fahrenheit. And so that's the purple line here is the temperature of the body at the time of death. The green line is the temperature of the room, and the red line is the temperature of the body as it cools off. And of course we can see back here where it crosses, looks like about an hour and a half before based on this graph, but we'll get a more little bit more precise measurement here as we go, under these assumptions, of course. So if we put in 98.6 for the temperature, and then we can solve for the time. Subtract 68 from both sides, we get 30.6 equals 17 e to the kt. And we divide by 17. Rewrite as a logarithm. The logarithm of, natural logarithm that is, of 30.6 over 17 is the power on the right, which is natural log of 12/17 times t. Divide both sides by the coefficient of t to get t is the natural log of 30.6 over 17 divided by the natural log of 12/17. And I did that on my calculator, as you can see down here, and got negative 1.68755, etc. hours. So in other words, about 1.7 hours earlier. Well, okay, let's convert that to hours and minutes. Okay, so first of all, I'm just going to forget the negative. I multiplied by negative 1 here in my calculator and got a positive 1.68 whatever. Then I took away the 1, so I know it's 1 hour. I want the decimal part to be in minutes. And there's 60 minutes per hour, so if I multiply 0.68755 whatever hours by 60 minutes per hour, I get the minutes, which is about 41 minutes. So it's happened approximately 1 hour and 41 minutes earlier. Well, 2 o'clock minus 1 hour and 40 minutes is 12:19 p.m. And so we found the time of death. Let me do one more example. This is an exact example off of that might be on your homework. A blacksmith immersed a piece of steel at 600 degrees Fahrenheit into a large bucket of water with temperature 65 degrees. After 1 minute, the temperature of the steel was 200 degrees. How much longer must the steel remain immersed to bring its temperature down to 100 degrees? Now we're assuming that the temperature of the, if we assume the temperature in the bucket stays 65 degrees, then this will work. In reality, if you stick that hot piece of steel into a bucket, the water's not going to stay 65 degrees. But let's pretend. Let's pretend that the temperature is going to stay the same. So the ambient temperature is, what was it? 65? 65 degrees, basically room temperature. A little bit cooler than room temperature, perhaps. So 65 degrees Fahrenheit. The initial temperature was 600 degrees Fahrenheit. Okay, so what's our equation? Well, our equation, remember, is the temperature is the ambient temperature plus the difference, T sub 0 minus T sub A, e to the kt. Now let's see, what do we know? We know this is 600 minus 65. That's my initial difference in temperature, is the coefficient there. And the this is the ambient temperature, 65. Alright, so that initial difference is 535 degrees, like that. So that's our equation, but we still don't know K. So to solve in K, we need some more information. We need another point. After 1 minute, it was 200 degrees. So it says when T is 1 minute, the temperature is 200. Okay, so 200 minus 65 is 135. That's e to the k. 135 over 535 is e to the k. So k is the natural log of 135 over 535. And notice I used 1 minute, so I'm going to have to measure my time in minutes now. Okay, take that, put it in place of k up here. So now my formula is T equals 65 plus 535 e to the natural log 135 over 535 T. We might be able to reduce that fraction as well. In fact, I know we can divide a 5 out. Okay, so there's our there's our formula. Now we have our formula, we can answer all kinds of questions about this. We could also graph it. How much longer does it need to get down to 100 degrees? Okay, well, 100 degrees here, we want to figure out the solution to this equation. That's the power. Okay, 100 minus 65 is 35. Well, that's the power. Divide by 535. 35 over 535 is e to the power. Take the logarithm now to get to our whole of power. So this is log base e of 35 over 535. When we take the logarithm this side, it all cancels, leaving just the power. Divide by this coefficient to get t by itself. It's natural log of 35 over 535. Divide by natural log of 135 over 535. Okay, and we might be able to reduce those fractions, but let's get a decimal approximation for this now. Natural log of 35 over 535 divided by a natural log of 135 over 535. Oh, wonderful. Calculator stopped on me. Let's see if it'll get it started again. Natural log of 35 over 535 divided by a natural log 135 over 535. About 1.98, and that's minutes. So about 1.98 or 2.0 minutes. Let's see how they want us to round off the answer. Nearest tenth, 2.0. Alright, let's check that. What? How much longer? Not the total time. Okay, so one more minute then. How much more does it go? One more minute than it was. Total of 2 minutes, one more minute. There we go. Alright, have to read the question carefully. How much longer does it take? Alright, so there's an example of that in the homework. And so now we've talked about Newton's law of cooling. There's the basic formula for it right there. So that's the basic formula. Okay?